So this is my last video of the semester. As you can see, we are taking a look at creating a study guide. And the first thing I want to tell you is that I used the midterm study guide to create this, and I changed the import SciPy stats. We didn't have hypothesis testing when we originally did this midterm, so it's kind of key to import it just like we did for the project. I wanted to do that to kind of keep everything the same. So I imported scipy.stats as stats. So I changed the import line on my midterm study guide. And then I just want to point out the most important thing on the exam is getting the rejection criteria correct. And if we have a p-value, I want you guys to be careful about this. If we have a p-value of 3.3 and then there's a bunch of numbers, but at the end we get the e to the minus 12, right? When this means it just switched to scientific notation, right? That's the computer's way of saying times 10 to the negative 12th. And even though the 3.3 part is greater than 0.05, this p-value, because of the scientific notation at the end and the negative exponent at the end, it is less than any sensible alpha that we would use, right? So ignore the fact that it has a larger than alpha start and check the end. Be wary of this scientific notation trick where it has lots of digits and you see and you fail to pick this up. You know, your eyeballs just don't go to the end of the number. So you want to check that, right? And make sure that you get this inequality correct. I am sorry, but there are going to be times when you have to judge correctly. And if p is less than alpha, we reject the null. Remember that a standard alpha, if you're not given any other information, then you can assume that alpha is equal to 0.05 or 5%, depending on how you prefer, whether you like the percentage or the decimal number, okay? But make sure you have your rejection criteria, and you can put it on your study guide, okay? If p is less than alpha, reject the null. Otherwise, fail to reject the null. That's the most important thing. That will cost you a lot of points. Unfortunately, I've seen it before, so I'm just warning you guys. Please get that rejection criteria correct. Put it on your study guide and do it right every single time. Please, please, please. I do not want you to miss those points. Okay, so the first thing I want to talk about is confidence intervals. And we could, for example, estimate the average level of perfectionism. All right. But I think it's more important, there's not going to be any coding on the final. There can't be because it's a multiple choice final. So what's going to be more important is understanding how to interpret a confidence interval correctly. And yes, this is how we create the confidence interval. And if you recall, there was a nice code block that calculated the confidence level for that we could put that in. It calculated degrees of freedom, the mean, the standard error, based on an array. We had to create an array and it would do all of this for us. Okay, so yeah, it's okay to review that and to put that on your study guide, but it's much more important to interpret this confidence interval correctly. Okay, and sorry, I'm going to go in here. I'm going to try to. All right, so hypothesis testing. And the reason I switched in here is because I put, okay, so we had researchers at UNG Dahlonega who selected 50 students at random, and they found students who live near but not on campus. They surveyed them about the cost of the rent that they had to pay for their college student housing in Dahlonega, Georgia. And what does it mean? Okay. So of course we use this to estimate the population mean. Okay, that's what it's used for. Sadly, that's not exactly what it means. Okay, let me open up a little code block here. And what does it mean? It means that we know, excuse me, we are, okay, I'll use we know. Okay, so we know that when we survey and 50 students. Why 50 students? Because that's how many were surveyed up here. So when we do this repeatedly, many times, so we know that when we repeatedly survey 50 students, their reported average rent will fall within the confidence interval 95% of the time. Okay, so let me make sure that that's in markdown mode so it will type out nicely. Sorry, it's still in code. There we go, markdown mode. All right, and I'm sorry, I'll pretty that up so you can see it. So, right, if the researchers selected 50 students, then we have to repeatedly survey the same number of students. And again, every time I do it for the 50 students, the average rent we find will fall within the interval 95% of the time if I have a 95% confidence interval. If I have a 90% confidence interval, it will fall within it 90% of the time. Okay? And next, we'll take a look at the t-tests. Okay? So we have two different kinds of t-tests. We have the straight up two-sample t-test, okay? And the way I know that is that I have the IND for independent, the independent samples t-test. What does that mean? That means that the samples are independent, so you cannot simultaneously be in both samples. So for example, you could compare people who are in an honor society to those who are not. So that's what we have here. Mu sub h, that's the average perfectionism score for the students who are in an honor society. And I just used not in, so capital N's. And so mu sub h equals mu sub n. The null hypothesis is that the averages are equal, and the alternative hypothesis is that there's some difference. Now, again, sometimes you'll see this as a less than, as a greater than. So there are other possibilities. But the big idea for the alternative is that there is some kind of difference. Okay? Difference in the means, and the null hypothesis is that the means are the same or approximately equal. Okay? So what do we do? Well, the key thing to remember is that this t-test runs on arrays. Okay? So the first thing we have to do is we have to create the array honor, which is the average perfectionism score for everybody who's in an honor society. And then I have to create this second array for all the students who are not. Okay, let's take a look at that. Sorry. Here, let's take a look at that here. So the very first code block creates arrays. All I'm doing is I'm using the dot where to select the students that we want. Where honor equals yes. Okay, so yes, I'm in an honor society. All right, and then I'm using dot column. Why? Well, I need an array. I want honor to be an array, so I use dot column and perf to get the perfectionism scores because that is the test that we're asked about. Doing the exact same thing to create the array not in. Here I have honor is equal to no, also using column perf. Okay, and then stats.t-test underscore independent, and I just put in the two samples, the two arrays for my two sample t-test, and you can see the p-value here. Okay, and so please notice that p is equal to, and let's go 0.717, which is greater than 0.05. Okay, which means we fail to reject, right? Which is no evidence of a difference. Let me type it in that way. No evidence of any difference in the group means. Okay, so what do we find out? We found out that perfectionism scores don't really vary too much based on honor societies. So honor society students are not more or less perfectionistic on average than students who are not in honor societies. The perfectionism, some of them are perfectionistic, some of them aren't, but it's not in any way more likely or less likely due to their participation in an honor society. Okay, so we don't find any evidence of a difference in the group means. Okay. The second type of t-test is this t-test underscore rel, and that's for a matched pairs or dependent samples t-test. So the IND means the samples are independent. Rel underscore rel, that's when I use when the samples are related. And a lot of times they're related like this example. Why? Because there's a pretest. Stress 1, this measure was taken in the second week of classes, and compare the same exact measure, which was taken several weeks later. Stress 2 was measured during midterms, when more students have midterms and papers and projects due. Okay, so we were asking about the stress levels. And so notice that I put in a mu sub g because I'm looking for the average gain score. All right, so our gain scores, if you think about it, are post minus pre. And sorry that it's taken me a while to type, or excuse me, to write. And I'm not doing it very well, sorry. Post minus pre, okay, you can kind of read that, and I apologize. So these gain scores are post minus pre, why? Well, you know, if you make an 80 on the pre-test and a 90 on the post-test, what we're really interested in is how much you gained. And you gained 10 points, the 90 minus 80. So it's post minus pre will get me the gain score. And then, of course, we anticipated a positive gain. Why? Well, we expect the stress 2 to be higher. Why? Because it was taken at midterms. We think that there is academic stress that's making people more stressed out than they were during the second week of the semester. Okay, and the key thing is we have to make these arrays. All right, that's another key. We have to put in arrays. So I'm going to create S2 for stress 2 and S1 for stress 1. Let's take a look at that. Okay. And so this is just taking stress 1. It was measured for everybody, so I can just do pers.column stress 1 and pers.column stress 2 to get my stress 1 and stress 2 measures, and then notice the p-value. Now the p-value is small, right? So since p equals, and let me get what, 0.0157? Yeah, 0.01571. Okay, and that's less than alpha. It's less than 0.05, and they haven't really specified anything, right? So we're going to use the standard alpha of 5% and reject the null, which indicates there is an increase in stress during midterms. Okay, and I say which indicates there is. Maybe I should say which means we have evidence there is. Okay, so we never really prove anything with statistics, and it's kind of sad. Even with really, really small p-values, we really just say we have evidence for something or another. Sometimes we have really, really strong evidence, but it's good to kind of leave this just a little bit equivocal. Okay, and then let's take a look at the chi-squared test, please. Okay, so we have two kinds of chi-square test, and the first one is chi-squared goodness of fit. And by the way, you'll see this as GOF, okay? And then we have the chi-squared test of independence, all right? What do? Well, the goodness of fit, it always tests a probability model. I have to have some way of coming up with the probabilities that certain things will happen. And then I collect observed data in all those categories and see how often they actually do happen. So I'm comparing observed data to a probability model. And the probabilities have to be given to me. I have to have some way to figure them out. I can't just be guessing. I mean, for example, I can have a fair die and I know that it needs to be 50-50 heads and tails. Or, excuse me, fair coin would be heads and tails. Fair die would be 1 6 1 6 1 6 for all 6 sides showing up. My bad for misspeaking there. Now, what does test of independence do? Okay, it compares two categorical variables to see if they are related. And in statistics speak, we call that relationship a dependence. Okay, so remember that your linear regression, your scatter plot in linear regression, checks to see if two numeric variables are related. The chi-square test of independence checks to see if two category variables are related. If category variables are related, we call it a dependence. And if numeric variables are related, we call it a correlation. Okay? So what we did in class was the eye color experiment, and let me show you that. Okay, so let me explain this chart. So this is actual data that I got from the American Academy of Ophthalmology, and this was the data for the year 2014. And the first thing I need to say is this doesn't matter. Sorry, let me scroll up just a little bit so you can see. Sorry. So this includes all races and ethnicities. And by the way, it turns out that all races and ethnicities can have all colors of eyes. So obviously there's different percentages and proportions depending on race, but it turns out that that these different categories are available regardless of ethnicity or race. Okay, so this was what it was. So what we do is we say, look, we're going to use this as a probability model for a class of students in 2024, and we're going to say, look, the probability of blue-gray irises, blue eyes, is 32%. And the probability of hazel eyes is 15%. Okay, so we're going to use the probabilities here, and we're going to compare them to a class of students. Okay, so here it is in Python, and please remember that, right, goodness of fit, GOF, is always testing a probability model. Okay, so we've got to do two different arrays here. We have to have the array, and this is what it was. We had 17 people in class, and these go in the same order that they were in the, eye color distribution chart that I showed you. Okay, and then these are the percentages from the eye color distribution chart, and I multiplied by 17. Why? Because there were 17 students, so we don't want percentages, we actually want counts. So we're correcting the counts based on the number of students that were there to be surveyed, okay? And when we run this, we get a p-value of 0.367, which by now I hope you know, since p is not less than alpha, we are going to fail to reject the null. And so that means that the probability model, we have evidence that the probability model is correct. So chi-squared GOF is a little backwards. Okay, usually we're trying to reject the null. Usually the research conclusion is the alternative hypothesis, and usually we want to reject the null and get a good research conclusion. But in this case, we actually want to fail to reject. Why? Well, if we reject the null, we're rejecting the idea that the probability model works. Okay, so we reject the null, we reject the probability model. When we fail to reject, like we do in this case, we say there is no evidence that the probability model is wrong. Now notice, these aren't exactly the right percentages, but they're not different enough to say, hey, throw out the probability model. It's working okay. The probability model works okay. Now, the second type of chi-square is the test of independence, where we compare two category variables, okay? And what we're going to do is we're going to compare sit class to honor. We're going to see, if the, wait, did I get this right? I'm worried that the, okay, I did do it right. I did sit class and honor. I was worried that I didn't do the correct category variable. What do we do first? Well, the first thing we do is this table method pivot from before the midterm. This was on our midterm study guide. Why? Because I need this. I need this pivot table. Why? Because I have to put it in. So this is what I need. I just need the observed data to go into the chi-squared goodness of fit. It will calculate this thing. You can see down here, it actually calculates an expected matrix, but it does that all on its own. Okay, so what's this? This expected matrix, these are the counts that you would expect if there is no connection between the two category variables. Okay, and basically what we're doing is we're comparing the observed data to what we would expect if they were completely independent. All right, so we get the observed data in. It's a matrix, I suppose. It's right. It's a 2-row array, an array with 2 rows. And then you just run it as chi-square or chi2 underscore contingency. And I just want to say that that's an old stats term for this matrix. It's called a two-way table. Why? Well, it's got one category variable down the columns and one category variable across the rows. So it was called a two-way table. Sorry about that. Okay, so it's called a two-way table, and those were also called contingency tables. So this is just a throwback to some of the old language that was used. Okay, and what do we find out here? And this is why the hypothesis testing help sheet is so nice, because it has little print statements at the bottom that kind of pretty this stuff up. And what happens is the p-value is right here. Okay, and I said the expected matrix is here. But this is our statistical conclusion. P is greater than 0.05, our standard alpha, so we fail to reject the null. And we do not have any evidence of a dependence between these two variables. So what did we learn? Well, that people involved in an honor society don't want to sit in the front, middle, or back any more often than the rest of the students at UNG. It's just not a thing. There are honor students sitting in the front, the middle, and the back, just like there are regular students sitting in the front, the middle, and the back. Okay, so ANOVA. So I would really like you guys to connect the idea of a t-test, a 2-sample t-test in the ANOVA. Why? Well, a 2-sample t-test can, believe it or not, only handle 2 groups. But the ANOVA can handle more groups, okay? So I like using the sit class variable. And we need a numeric variable. So we're going to see if the numeric variable is different based on the category variable of where they like to sit in class. Now, the null hypothesis is that everything is the same or equal. Right? So like I said before, same is the null hypothesis. That's the big idea of the null hypothesis. And the big idea or the alternative is that no, there's a difference in group means. So the null hypothesis is that all group means are approximately equal, they're the same. The alternative is that at least one group mean is significantly different than the others. Okay, and I did not load group stats, I don't believe, so I'm not going to be able to do that. So I'm going to create the arrays for the 3 groups for front, middle, and back. And to run the ANOVA, I just put in the arrays. And so if I have 15 groups that I'm comparing, I have to make 15 arrays and put in 15 arrays. Unfortunately, it's not a table method. I can't just tell it the columns. I have to go in and create arrays for every single group that I want to put into the ANOVA. Okay, oh, and by the way, I forgot to mention this. Let me jump into this ANOVA. I'm sorry. Trying to get in there. Why? Well, if you put hashtags to start a markdown cell, it will be level headings. And so the bigger level headings have, so that's a first level heading, boom, it's big. And second level headings, 2 hashtags. Okay, again, if you make it markdown and start with hashtags, it will give you a heading. Okay, and I already said this. We were looking at the other slide. So to test the GPA, test for GPA differences based on sit class, what did I do? Okay, just like I said, I need a front array. So I did where sit class is equal to F, and then a dot column to get all the GPAs. I did that for middle and back. And then I ran the F underscore one way, which is the one way ANOVA, using the front, middle, and back arrays. And notice that the p-value is just slightly less than 0.05. Barely. Okay, so apparently there is a difference in GPA based on where people prefer to sit in class. I don't want to go too deeply into this. This is not a highly significant result. It doesn't mean, and first of all, a lot of you guys listening to this video are online students. It doesn't matter. You can't have a front, middle, or back of an online class. But I don't want people to worry too much about this. It's not deterministic. Okay, it's self-reported GPA and self-reported preferences of sitting in the front, middle, or back, and the p-value is just barely significant. So it is interesting, and if you'd like, you can do the means. You can do NP average for front and NP average for middle and NP average for back and see which has the highest average GPA if you'd like to do that. But again, don't put too much weight on it. And then linear regression, and let's just go over this real quickly. Again, we're comparing 2 numeric variables. In this case, we had a measure of optimism and a measure of thrill seeking. They're both numeric, and we're checking to see if there's a correlation between them. But the first thing we do is a scatter plot, which, by the way, is a table method. All right, and then we create arrays. Why? Because when I run the linregress, the stats.linregress, I need arrays. Okay, so let's check out how that looks. Okay, so first we just run the scatter plot, and we almost always suggest putting a fit line equals true in there. Why? Well, this one was the case. We could probably have seen there was some kind of a relationship, but it's a little fuzzy exactly what the relationship was if I leave the fit line equals true off. If I put the fit line equals true in, it becomes pretty clear. Okay, there's a positive association, right? We don't know if there's a correlation yet. We're going to run the linregress in just a moment to check. But we appear from the scatter plot to have a positive association, meaning that as optimism scores up, thrill-seeking behaviors increase. And as thrill-seeking behaviors decrease, optimism levels go down. Okay? And we observe the positive linear association in the scatter plot, so we conduct the linear regression. And all I did was take the optimism column and make it an array called OPT, and the thrill-seeking column made it an array thrill, and I did opt on the x-axis. Why? Well, because in the scatter plot, optimism was on the x-axis. Okay, so this will just match up our results if we do them in the same order. Okay, and notice that we do get a positive correlation of about 0.3. So that's a pretty weak correlation. I'm not saying that it's not a good correlation, right? The p-value is actually much lower than our standard alpha. The p-value is 0.0005. So since p is less than alpha, as you can see the reporting out down here, we reject the null. What does rejecting the null mean in a linear regression? It means that we have evidence of a significant correlation between optimism and thrill seeking. Okay, we also know that the correlation is positive. Why? Well, if the slope of the fit line is positive, the line of best fit is positive, then the correlation will be positive. And again, when the correlation is negative, they will have a downward sloping fit line. Okay, so I went through those pretty quickly, and I wanted to get to some additional questions. Why? Well, again, you're not going to be coding on the test. Is this important? Well, you should recognize it. It'd be good to have an example on your study guide if you'd like, just to remind you of how it goes. That's great. But there are going to be questions like this on the test too, and I wanted to go over some of them. Okay, so they're going to ask you about which hypothesis test you should use in a particular situation, and they'll ask you about p-values and what your research conclusion should be. Now, I wanted to give you some examples, okay? This question actually began about 15 years ago when I had a student who was interested in Dobermans, and apparently the Dobermans that have fawn-colored fur are considered the most rare, and therefore they are the most expensive. And this student of mine was interested. He was looking at a breeder's website, and he was hypothesizing about this genetic model. What are the chances that if I breed my dog to this dog at this, that the breeder website is advertising, what's the probability that the pups will be born? And in his case, he wanted fawn-colored coats, but for example, maybe there's a 25% chance that the dog should have blue eyes. Okay, test whether the genetic model is correct. And by the way, if you're a biology major, just listen carefully. This happens all the time in the genetics class. You use, what do you use? Goodness of fit. Why? We're trying to fit this genetic model. Now, a lot of times the model is a guess. Now, it's a guess based on information, right? You have information about your dog, you have information about the dog from the breeder's website. You get as much information as you can, and then you guess what the genetic model is. How do you tell? Well, the pups that are born, you track what percentage of them have the criteria that you're hoping for. Well, actually, you check all the criteria that you have in the genetic model, but you check to see. So this is a chi-squared goodness of fit, and I just want to let you know there will also be questions like the following. So P equals 0.82, which do we do? Reject or fail to reject the null? And I just hope that you immediately jumped on this one. Why? Because P is much greater than the standard alpha of 0.05. And even if we used a different alpha like 0.1 or 0.01, still the p-value is going to be much greater, and we are going to fail to reject the null. What does that mean? Remember, that's good in chi-squared goodness of fit. If we reject the null, we're rejecting the probability model. But here, let's just say that this person is really interested in dogs that have blue eyes, so they want their probability model to be correct. So this is good news that they fail to reject the null. Therefore, we have no evidence that the genetic model is flawed. Okay, let's take a look at another one. And you should probably pause the video, read the question, and answer it yourself right now. Okay, I'll give you a couple of seconds to do that. Okay, so they're testing a medicine for migraines, and they compare a treatment group to a control group. What is the correct test? Okay, well, the key to notice is that there is one group and there is another group. So we have one group that's getting the placebo or the sugar pill. We have another group that's getting the active medication. So we have two groups. This is a two-sample t-test. Is it matched pairs? Okay, well, the key is whether or not, in this case, the samples are independent, or in this case, whether they're related, right? That underscore REL, related or matched pairs. And they're not. They're different people. If there are 50 people in the study, then 25 are randomly selected to get the medicine, and the other 25 are randomly selected and they get the placebo. So a person cannot simultaneously be in both the treatment and the control. So the correct answer is 1. Okay, you should probably take a couple seconds to try to answer this question. So pause the video if you need to. We're going to reject the null, right? This is less than 0.05, which is our standard alpha. So we're going to reject the null. And then what about this question? So in the above study where we're doing medicine, a treatment versus control group for medicine, which is correct. Okay, so we have this 0.0168 p-value. So do we decide that the medicine is effective or not? And when we reject the null, okay, so if you if you remember, the big idea for the null hypothesis is that the means are the same. Okay, and same means that the treatment group only experienced the same amount of relief for migraines as the control group, the group that was taking a sugar pill. This is not what we want to happen. If we're a pharmaceutical company that's testing a new medicine, we desperately want to reject the null, because that's the only way we're going to sell that medication and make any money, okay? So when we have this p-value and we reject the null, that's good news for the drug manufacturer. And we do have evidence that suggests the medicine is effective. So treatment versus control group, we really do want to reject the null in that case if we're the pharmaceutical company and we'd like to make money on the sales. And one final example, researchers are comparing seating preference in class to whether or not a student is an honor society and which hypothesis test should be run. Well, we've already run this. What did we run? And it is a category variable seating preference. And is a category variable yes or no if you're in an honor society. Sorry, I didn't mean to scratch that out. I was trying to underline it. So when I'm comparing two category variables, what do I use? I use the chi-squared test of independence. Okay, so I just want you to be ready to be thinking about these examples 1, 2, and 3 that I've given you, because these types of things will in fact show up on the exam. Okay, so I've covered what you might want to put on your hypothesis testing part of your study guide. And also I've gone over 3 examples. So what I'm going to do is I'm going to post both of these, the PDF and the video, in the announcements, so that you can come back and get any of the words that you need that you might have missed on the, it's actually an Adobe PDF file that I will post. Okay, want to say good luck to everybody on the final exam, and good luck on all your finals, and Merry Christmas.